Hello, welcome to another Teachertopia tutorial. We're going to be talking about character encoding from topic 2, the data topic. The reference will be 2.2.1, and this is related to GCSE Computer Science Edexcel specification. So anytime you hit a key on the keyboard, that character corresponds to a binary code, and there is a character map that is used to map all the different binary codes, and we'll have a look at that in just a second. Just before we move on, a potential misconception that GCSE students have for Edexcel is that the ASCII specification that might come up in an exam is extended ASCII, which is something different. Extended ASCII was a newer system developed to include more characters, and it uses 8 bits. Right? Original ASCII has 7 bits, and I'll show that to you in just a second when we look at that chart again. And now we would be encoding with something called Unicode, which has backwards compatibility for ASCII. So you might have most websites with the character set UTF-8, which will cover most languages. So ASCII's big limitation was that it could only really have the Roman alphabet, and you don't have any tildes or anything that's particularly useful for other languages. And extended ASCII helped to rectify some of that, and of course now with Unicode we can have support traditional Chinese characters and all sorts of other languages. But the original ASCII standard is what you'd ever get in an exam. So from 32 onwards is all the printable things, up to say the delete key. So you can see here it says decimal 32. So what would that be in binary? Well, if I put our columns for binary values here, 32 would just be that column switched on. And if we split it into 2 and look at the nibbles, that's 0. And if we look at this as 8421, that would be a 2. So in hexadecimal, we're looking at 20, base 16 version of that, base 2. So let's have a look. There you go. The hex representation in base 16 for the space character on the keyboard is 20, and the decimal is 32, and the binary, we just worked it out, 00100000. So anytime you hit the space bar on your computer, that binary number is what's being referenced, and this is standard across all devices, and all the computer manufacturers made sure that it was standard across all their devices. So this creates some interesting things here, because if we go back, you'll notice that we've got capital A here, and then we've got smaller a here, but the number for that is actually for the capital letter is a smaller number than the lowercase, and also the numerical the numbers 0 to 9 don't match up with their binary equivalents, which is why when we're doing programming we can't use the strings for calculations. We have to convert it to an integer. If we type in a number, we have to make sure we're converting that data type into an integer, because the reference for those numbers isn't going to be correct. So a typical exam style question, which we'll have a look at, might be this. An ASCII code for the character H is 72 in denary. Okay. Derive the ASCII code character for E. All right, so for something like this, the easiest way of doing this would be to say H is 72. Okay, so E, F, G, H is the alphabet, isn't it? So if H is 71, H is 72, G 71, F is 70, and E is going to be 69. And it's asking you to do it in 8-bit binary. And as I told you, the ASCII standard is actually 7 bits. So you just put a 0 at the beginning. Just put a 0 at the beginning. Because that will be reserved for the computer. Because early computers were only dealing with a byte at a time. They were 8-bit computers, so they reserved the most significant bit there for other things. And they had only 127 here as the positive, the largest positive number available in 7 bits, and the lowest there's 0. So in total, what we have there is 2 to the power of 7 equals 128 patterns, unique patterns. That's the largest positive integer is 127, and 0 is 128 different patterns. So we were limited with the early ASCII specification that we could only have 128 things, and that's what they chose. Okay, so let's go back to our question. Derive the ASCII code for the character. So we know now what the denary number would be for E, so we just need to now represent 69 in binary. So let's just put our values up here. Okay, does 64 go into 69? It most certainly does, so I'm going to have that one turned on. That turned off. What else do I need? I need a 5. So I just need the 4 and the 1. And that would very likely, because it's a 2-mark question, it would either be marking for each nibble or the fact that you derived the denary number and then got the binary number. But either way, you need to do both things to get the correct answer for that exam question. Let's have a look at another exam style question here. 1 byte, which is 8 bits. You should remember that a byte is 8 bits. Is used to store 1 character. Right? The leftmost bit of each byte is 0. That's what we just talked about. State how many bytes are required to store the phrase slow down. Okay, so we need 1 byte here to store the S, the capital S. We need another one to store capital L. We need another one to store the O, and we need another one to store the W. Now, what a student might do is say, okay, well, we just need 8 bytes for each character, which would be wrong, because the space is its own character. I mean, we've got it's its own character, so we've got to have a space for that allocated in our bytes, 6, 7, 8, and 9. So to have the phrase slow space down, we need to store that within 9 bytes. It would take 9 bytes to store that phrase. And you can have a look at here, if we look at capital S, that's what the binary number would be to store the capital letter S for that phrase. So let's just quickly talk about some interesting things that might come up when we're doing more programming with ASCII. We can do within Python, we can use odd and then put a string in there as a parameter, and that will return, let's have a look, small c should return the position on our character map of that ASCII character, which is 99. So let's say we printed out odd C, we would get in our console 99. So we can find out the position of any character in Python. We can also do the reverse as well. Let's say we knew the position, but we didn't know what the character was. So we could put CHR for character. These are all built-in functions in Python. We could put the position in there, and that would equate to, let's have a look. I think it's D. Yeah, there you go. Because 67 is lowercase a. So that would result in the string D being output if we printed it out, of course. So you can use that to sort of reverse engineer, if you like, the order of a key. Now this would be useful in something like a Caesar cipher where we're shifting positions, and we want to know what the order of the alphabet letters are, and we want to shift it over by one. That could be particularly useful for that. What else could we do? We could, well, another thing that's interesting, if you printed out string A less than string A uppercase, what do you think the output would be of that? And let's have a look. Small a is higher up on the table than our capital A, which I think is at 65. So, yeah, so 65 there, but the lowercase a is actually bigger. So to say that it's less would be a false statement. So it would look at the position of the string, the character, in the ASCII map and think, okay, which one is less than the other? And you can do relational operators like that with ASCII characters and strings in Python. So that would output false if you did that. And conversely, if we change that to greater than, it would give you true, because small or lowercase a is bigger than uppercase a in terms of the ASCII position that it's in. So let's look at another scenario where, let's say we've got a string, and it's a Disney Once Upon a Time opener. Let's say we've got that string, and the question might be something to do with print out the ASCII codes of each character in that string. All right, so we're going to need to iterate over each character in that string and figure out what the code would be, the position number, and have them printed out. So an iterator loop would be a for loop. So we can have a for loop, and then we could say for, try and use different colors, for index in range and here we want to get how long this is. We don't know how long it is, so we can say the length of my string, colon at the end, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That'd be 16 because I include the spaces in that as well. So the for loop would iterate over each one of these in turn, and then what do we want to print out? As this is a procedure, it's not a function, we're just going to print it out. we're going to print out the ORD of my string, and then we want to use as our index position the number that we're generating each time the loop goes round. And that would allow us to, because index is going to start off, we count from 0 in Python. This O for once is at position 0, N is at position 1, and then the E is at position 16 if I counted up correctly. Apologies, 15. It would be at position 15 because we start from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So lowercase e is at position 15. Let me write that again. The length is 16, but we count from 0. So the for loop, the index value will be 0 when the loop first goes round. That means it will look at 0. My string index 0 will point to that big O, and it will look at big O. Where is it? And it's 79. So output on the screen would be 79, and then the index value would be then 1, and we look at 1, and that would be small n. So we look at n, and that would be 110. So the next number would be 110, and it will keep on going, and it would print 16 different numbers. So let's do one more of this. So at index 2, lowercase c, which is at decimal value 99. So we get 99 when we get printed out on the screen. And let's say you had a kind of question that says the character index 2 returns number 99, which is what we just figured out. And index 3 returns 101. What would be returned at index 8? Okay, what would be returned at index 8? So let's just have a look. Index 0 is our big O, index 1 is N, index 2 is C, index 3 is E, index 4 is our space, index 5 is U, index 6 is P, index 7 is O, and then index 8 is our lowercase n. And let's find lowercase n. 110. So the answer to that hypothetical question would be 110. Hopefully this helped you a little, and if it did, let me know. If it didn't, let me know, and I can do more on this if need be, especially with the Python. Sometimes it's hard to just go through the theory without doing a little bit of Python, because there are 2 papers for the Edexcel exam. They're 50% of the marks, 2 hours for paper 2, 1.5 hours for paper 1, 50% of the marks. So it's understanding how we can apply some of the theory into algorithms is going to be useful. So if I confuse you with the Python, don't worry about that too much. It shouldn't stop you from answering questions in paper 1 about the ASCII table and looking up numbers and so forth. See you next time.